In this lesson, we will dig into the basics of resistors. We will learn their properties and also how to simplify circuits built with them. The following image shows a basic representation of a conductor. It can be a piece of wire or a cylinder. If we put voltage across its terminals, we know that it will induce a current that will flow through it. Metals are very good at conducting electricity, unlike other materials like wood or plastic. The resistance of a wire like the one in the picture, it is in terms of the area A, the length of the wire L, and the type of material. Each material has a resistivity value represented by the letter ρ. Most metals are good conductors, which means that they have low resistivity. One thing that we can see from the formula is that as the area increases, the resistance of the conductor is reduced. The reason is that the larger the area, the more space or atoms have the electrons to flow. But when the length increases, the resistance increases. That's because electrons have to cross a longer distance. A metal like copper has a resistivity of 1.68 to the power of -8, and that's given in ohms per meter. A metal like silver has lower resistivity, therefore it is a better conductor. However, silver is more expensive than copper, and for that reason copper is more often used. One term that we will find often is the conductivity. The conductivity is the reciprocal of the resistance. It is a measure of how good a material is to conduct electricity. Similarly, there exists the term conductance, which tells us how good is a conductor to conduct. The conductance is the reciprocal of the resistance, and the units are mhos, which is the word ohm backwards, and the symbol is the same as for the ohms, but upside down. Now let's determine what happens when we combine multiple conductors. The first case is connecting one after the other. This is shown in the drawing. This kind of connection is called series connection. We can see that if we connect two similar conductors, the effective length doubles. This makes the total resistance twice the resistance of a single conductor. One important aspect to consider is that the same current flows through both conductors. In this case, it is represented by the symbol I. But what happens when the conductors have different dimensions or are made of different materials? In such case, we can use the general formula that tells us the equivalent resistance of two resistors in series, and that's simply the sum of both resistors. For multiple resistors, we can sum the resistance values of all the components. A second way in which we can connect multiple components is the following, which is called parallel. The two terminals of the conductors are connected to each other. In this case, we can see that having two conductors doubles the area. Since there are two paths where the currents can flow, part of the current goes through one conductor and the remaining goes through the other one. The general formula for calculating the resistance of two conductors in parallel is the following, which is easier to remember if we use conductance instead of resistance. When multiple conductors are connected in parallel, the total conductance is the sum of all the individual conductances. Since the conductance is the reciprocal of the resistor, we can derive the formula for the equivalent resistance. And after simplification, we can see that in order to calculate the resistance, we are summing all the conductances and then getting the reciprocal in order to obtain the resistance. You will often see the following symbol used to represent the calculation of the parallel of two resistors. It is two small parallel lines. For two resistors, we can obtain the following formula, which is easy to remember. The parallel of two resistors is the multiplication of the two values divided by the sum of the two values. If we have more resistors in parallel, we can calculate them pair by pair. For example, it would be similar to calculate first R1 in parallel with R2, and then the result will be in parallel with R3, or R1 in parallel with R2 and R3 in parallel. When we are faced with more complex networks of resistors, we use a divide and conquer approach. we need to find smaller groups of resistors connected in series or parallel and replace them by their equivalent resistor. For example, in the following diagram, I have marked such groups of resistors. We can see that if we want to calculate the equivalent resistance for this, we have this group, which is R7, 6, and 5, the three connected in parallel, then connected in series with R8. And on the bottom side, we have R1, R2 in parallel, which are then connected in series with R3 and R4. And then we have these two groups, which are connected in parallel. And here we have the equation that represents all these calculations. To summarize this lesson, we learned that the resistance of a conductor is determined by the resistivity of the material and the dimensions of the conductor. We can obtain the equivalent resistance of two resistors connected in series by adding their individual values. In the case of parallel resistors, we can add their conductance values, which is the reciprocal of the resistance. Complex networks of resistors can be simplified using those two formulas.